All right, so we're not going to go straight into the pod at first. Instead, we're going to talk a little bit about synthesis. This is material from Chapter 12, but it's very, very useful for Chapter 9 and 10. And one question I hear a lot from organic students is, why does synthesis matter? Can't we just make everything? Not really. So here's an example I have for you guys of a compound that was isolated from a sea sponge. This compound kills cancer cells at the picomolar level. It's an incredibly potent anti-cancer drug. The problem is, it takes, 1 ton of sea sponges to make 400 milligrams of this drug. So unless we're going to go out and kill every single sea sponge on the planet, we have to figure out a better route to making this, right? And the other tricky thing with this is there are 32 different stereocenters in this molecule. This would be a good exam problem. Label all the stereocenters as R and S. And so if you factor out the number of stereoisomers for this drug, there are 4.2 billion approximate stereoisomers, which means making this thing is a bear. There was a group at Harvard that recently decided that they were up to the challenge, and they were able to make this in 47 steps. So in your problem of the day, you had 4 steps. Can you imagine going backwards 47 steps? It's doable, but it takes a lot of practice to get good at planning synthesis. So I'm going to show you guys this brief crash course for planning. Most of it's fairly intuitive. But the first thing you want to do before starting the synthesis is determine if the number of carbons changed from your starting material to your final product. If you gained carbons, that means you probably did some sort of SN2 alkylation. We're later on going to learn more reactions with things like Grignards where we can add carbons. But as far as we're concerned right now, the only way we have of adding carbons is SN2 chemistry. If we're losing carbons from starting material to product, that means we're probably doing some sort of ozonolysis reaction, right? Because if we do ozonolysis, we're splitting a triple bond or a double bond.
I thought you could add carbons by adding an R group to like a triple bond.
Yeah, that's alkylation.
Okay.
So it's still via an SN2 mechanism with an acetylide ion. That's your deprotonated triple bond. But it's still via SN2 route. All right, the second thing you want to do is determine if your functional group has changed and if it's at the same or in a different position. Really, these are the 2 basic rules, and I told a lot of you that came to my office, start with your final product and work backwards 1 step at a time. One really valuable trick for organic chemistry is to create reaction maps. So if you look at your problem of the day, that's a reaction map for this chapter. If you go through and practice making reaction maps and try to tie concepts together, you'll retain that information a lot better. What I call reactions that we've learned are our reaction toolbox. So you can see we've covered substitution, elimination, alkene addition, alkyne addition, and next chapter we're going to do radical addition. And then we've got all these tools to interconvert functional groups. So we can go from an alkane to a haloalkane. We can go from a haloalkane to an alkene. We can go from an alkene to an alkyne. And we can flip-flop in between all of these now. We've got a bunch of tools at our disposal. So the goal is to have you guys down pat with Chapter 10, Chapter 9, Chapter 8. We're going to cover Chapter 11 next, and some of Chapter 11 will be on the final. But we need to make sure that we've got these reactions down because that's essential for planning synthetic routes. Does that make sense? I'll show you guys really quick. You don't need to take notes on this unless you really want to, but I'll show you kind of my thought process when I plan a synthesis.
Should we put the 11 on the exam first?
Yeah, some of the radical chapter will be on the exam. The trick when planning a synthesis is doing something called retrosynthesis. That means planning your reaction backwards, just like many of you are doing. And oftentimes you'll see a different looking arrow where instead of having just a normal looking arrow, you actually have something with 2 parallel lines and an arrowhead. That's for retrosynthesis. It's basically like a backwards arrow. So you can have your product on the left and your starting material on the right and just work backwards step by step. We're going to practice this a lot more. But the key is to focus on functional group transformations, and you want to use that reaction toolbox that we've been developing. The other thing with synthesis is some routes may just be dead ends, and that's perfectly fine. If you run into a dead end, just cross it out and find an alternate route to continue working off of. So let's take an example here. So in this example, I want to make the alkyne on the left, and I'm starting with the alcohol on the right. So now the question is, how can we make an alkyne? Does anybody have an idea?
Alcohol group and then having two elimination.
So one thing I would say is ignore the alcohol for right now. Cover that up, ignore it. It will confuse you. Just focus on the alkyne. How can we make an alkyne? What intermediate can we use to get to an alkyne? Does anybody have an idea? Not quite an alkene. We need something else. An alkane with 2 bromines. So a lot of you guys did that on your problem of the day, right? So we've got a question. All right, we can use a geminal dihalide. We could use a vicinal dihalide. We can even have a halogen coming off of an alkene, and we can do an elimination reaction to get to our alkyne. This is great. We've got 3 potential options. So we've worked backwards 1 step. The question is, which one are we going to continue working off of? So now we have to ask ourselves, all right, how can I make a geminal dihalide? Does anybody have an idea? Again, this is using our reaction toolbox. How can we make a geminal dihalide? We could use HBr and an alkyne, right? So we work backwards and we say, all right, now we need to figure out how to make that reagent, and we could make all of those 3 reagents using 3 different routes. So for example, if we want the bromine coming off of the alkene, we can add 1 equivalent of HBr to an alkyne. That will give you the bromine in that Markovnikov position. If we add bromine or HBr in excess, then we get double addition, 2 bromines. That's our geminal dihalide. And then if we use our alkene at the bottom, we could just do plain old halogenation with an alkene and get anti-addition of 2 bromines. If you think about it, we just came from an alkene. So which of these routes do you think is the best? The third one, right? Because we don't want to run around in a circle. We just went from these 2. These were our final products. We don't want to have our final product as an intermediate, right? So this is kind of a dead end. So we can cross these out and we can say, all right, this is a dead end. And we can work backwards. Now the question is, well, how do we make this guy, the alkene on the bottom? What ways do we know of making alkenes? Elimination. All right. So now we can look at a couple different routes. One route is elimination using a base, doing something like an E2 mechanism. Another route could be dissolving metal reduction or Lindlar's catalyst to go from an alkyne to an alkene. Which of these 2 routes do you think is the most promising? Yeah, the second one. So again, we don't want a dead end where we're using our final product as an intermediate. That's not really helping us. But we're getting somewhere now. Now we've got to figure out how to make this intermediate. So if you think about it, we know how to turn an alcohol into a leaving group using tosyl chloride and pyridine. And if you forgot what tosyl chloride and pyridine look like, you can use these 2 guys, and that turns our alcohol into a good leaving group. All right, so now we're all the way back at our starting material. Once I've done that retrosynthesis, going backwards from the product to our starting material, then I try to piece it all together and then kind of put it into one cohesive synthesis. So first step, turn that alcohol into a good leaving group. Second step, we want to do an elimination, so I'm going to use DBU. Third step, we'll brominate. Fourth step, we'll do a double elimination and quench the reaction with water. So it takes a while to get good at this. You can imagine that group in Harvard. It probably took them a few years, if not their entire careers, to plan that whole synthesis. So don't get discouraged if it's challenging at first. We're going to go through a bunch of practice problems today. But let's go back to our pod, and I want